I'm going to give a lecture on gravity today. So the concept of gravity was not so important until Sir Isaac Newton in 1664 saw an apple falling from the tree, and he was like wondering, why does this apple fall downward? So, and then he realized that everything released from top falls in downward direction. So he thought there might be some attractive force in the earth which attracts everything towards itself, and then he proposed the law of gravitation, universal law of gravitation, universal laws of gravitation. So let me quickly describe these laws. So he said every two bodies in this universe attract each other by a certain amount of force, and that force is called as the gravitational force of attraction. So whether any body having certain masses, it may be the small masses or the larger masses. Say we have two bodies of masses m1 and m2 which are at a distance of d, then this mass m1 is attracted by mass m2, and mass m2 is attracted by mass m1, and these have two equal and opposite forces. So the first law says every two bodies in this universe attract each other by a certain amount of force called as gravitational force of attraction. And the second one, so the forces between these two bodies are equal and opposite, so we can say that this pair is action reaction pair of forces, action reaction pair of forces. And the third one is, where does the force act along them? So this force of attraction between these two bodies act along the line joining the centers. So this is the line joining the centers. So the force of attraction act along this line joining these two forces, joining the centers of those two masses. And he also quantified the force, the actual value of the force of attraction. So he proposed a law where he said that this force of attraction between any two bodies in this universe is directly proportional to the product of their masses. So more is the mass, more is the force of attraction, and also inversely proportional to the square of distance between them. So more is the distance, less is the attraction, less is the distance, more is the attraction. And removing this proportionality sign comes a proportionality constant here, G, where G is a proportionality constant called as universal gravitational constant, universal gravitational constant, and whose value is 6.67 into 10 the negative 11, and G being the product of force and distance square divided by the mass square. Its unit is Newton meter square per kg square, Newton meter square per kg square. Now let me show you with a quick example, with two quick examples showing how the gravitational force of attraction vary with the masses. So if I take two small masses of 1 kilogram each, which are separated at a distance of 0.5 meter, then the gravitational force of attraction between them is, let me write here, the gravitational force of attraction between them is Z m1 m2 by d squared. So G is 6.67 into 10 d negative 11 times mass is 1 times mass is 1 times distance is 0.5 squared. On solving this, I already have solved this one. I don't want to waste my time. 26.8 times 10 the negative 11 Newton. So this is the force of attraction between these two small masses. Now let me show you an example where I take two big masses. Say this is the Earth and this is Moon. The mass of Earth is 6 into 10 the 24 kilogram, and the mass of Moon is 7.4 into 10 the 22 kilogram, and the distance between their centers is 3.84 into 10 the 8 meter. So in this case, the gravitational force of attraction is the gravitational force of attraction is again G m1 m2 by r square, where G is 6.67 into 10 the negative 11 times the mass is 6 into 10 the 24 times 7.4 into 10 the 22 divided by the distance square, 3.84 into 10 the 8 square, and this is equal to 2.01 into 10 the 20 Newton. So we can compare and see the force, the gravitational force of attraction due to these two small masses is just 26.8 into 10 the 11 Newton, which is very small. Whereas the force of attraction existing between the masses of Earth and Moon is 2.01 times 10 to 20 Newton, which is huge. So we can say that this gravitational force of attraction obviously depends on the product of the masses. Now, on this gravitational force of attraction, if any one of them is Earth, that means the force with which Earth pulls anybody towards itself is called as gravity, or the force of gravity. So all the bodies are attracted towards Earth. All the bodies are attracted towards Earth by certain amount of force, by certain amount of force, and that force is called as gravity, or the simply force of gravity. So now I'm going to let me write this equation first here. F equals to Z m1 m2 by d square, because this is the gravitational force of attraction and it is very important equation here. Now I'm going to explain a little on the force due to gravity. Say this is Earth and this is any object close to the Earth's surface of mass m. This is Earth of radius re. So as I already said, any body allowed to falls towards the Earth's surface. So Earth has a gravitational pull towards itself. That is called the force of gravity. And I'm going to find out the acceleration due to gravity on the Earth's surface or close to the Earth's surface. So a body of mass m on the Earth's surface of radius re, then the force experienced by the body of mass m due to this Earth is F equals to G m1 m2 by d square by the gravitational law of attraction. Whereas the weight on this body, towards downward direction, or the force with which Earth pulls this one is mg, where g is the acceleration due to gravity, and it is always vertically downward direction towards the Earth center. So this force is going to be mg. G m1 is the mass of Earth, m2 is the mass of this small object, and the distance between them is re plus this small distance, but compared to the radius of Earth, which is the radius of Earth is 6,400 kilometers, that is 6.4 into 10 to the power 6 meters, is very, very large compared to this small mass. So we neglect the radius of this Earth, or its distance from the Earth's surface, times d square. Cancelling these two, I get gravity is Zm by d square. So the acceleration due to gravity on the Earth's surface or close to Earth's surface is Zm by d square. Now let me put the values here. 6.67 into 10 the negative 11. The mass of Earth is 6 into 10 the 24 divided by the radius of Earth is 6.4 into 10 the 6 whole square, and then you get 9.8 meters per second square. So the acceleration due to gravity on the Earth's surface or close to the Earth's surface is 9.8 meters per second square. That means any body falling in downward direction falls with the increasing velocity, where its acceleration is 9.8 meters per second square. Now let's see what would be the acceleration due to gravity at a height h from the Earth's surface. So this is a body of mass m at a height h from the Earth's surface. So I'm going to find out the acceleration due to gravity of that mass depending on the height. Depending on the height. So here, so again I use the same equation. G is Gm by d square. Gm by d square. G is 6.67 into 10 the negative 11. The mass is 6 into 10 the 24 divided by d. D is Re plus h. So you have Re plus h whole square. So let me write Gm instead of putting the values here. Gm. So Gm take RE out, 1 plus h by RE whole square. So this gives Z, this Z is due to height, so G h equals to, this is G, this comes up, so it's 1 plus h by RE negative 2, as this height is very small compared to the radius of Earth, so I can use a binomial equation here, and it gives 1 minus twice h by RE, and this is less than 1, so this so from here I can say GH is less than G. So as you go higher the Earth's surface, the acceleration due to gravity keeps on decreasing. Thank you.